given the number of students who are struggling with the material of metrics this term, and I'm talking about EC221, I have decided to create a series of videos to cover each of the subjects covered in the lectures in detail, without the constraint of time which the lecturer and the teachers are limited by. And hopefully this will create another source of receiving the information in another way, and hopefully help getting more students to understand the concepts. So I'm starting with a subject that was covered last week, at the end of last week, and I will carry on from there, covering more and more subjects every week as they are introduced with Dr. Shafkan's. So in this video I'm covering omission of relevant variables. I'm going to start with the meaning of relevant variables. So let's take the regression model, the partitioned regression model, y equals x beta plus z gamma plus d delta, plus of course the epsilon. Now, a relevant variable means a regressor whose parameter is not equal to 0. So which one is how can we decide which one of these is relevant and which one is not? Well, if delta equals to 0, and that's a vector, by the way, so this 0 is a vector. If this was the case, then delta is an irrelevant variable because it doesn't affect y. Remember, the parameters represent the marginal effect of a regressor on the dependent variable, which is y here. Now, if gamma was not equal to 0, then z is a relevant variable, and dropping it out of the regression has some consequences which we will cover in this video. And this is a good point to move on to what will happen if we drop out a relevant variable. So let's say that, okay, so we said that d was an irrelevant variable, so I'm going to drop it out of the regression. So the true model, and basically the phrase true model means is that y is related to these regressor in this way. So y is only decided by these regressors, and in the functional form provided in this equation. So the true value of y is this x beta plus z gamma, sorry, that's delta, gamma plus epsilon. Now I will dissect what this means. So I will start with x and z. So we are talking about x and z that are fixed. For example, what does it mean when a regressor is fixed? So think of an experiment. You get to choose what x and z are. Therefore, they're not random, they are fixed. So if you choose x to be, so this is a matrix, and if you choose your regressors to take certain values for certain pupils, this is a fixed value, not a random value. And therefore, it cannot take any value. There is only one value it can take, which is what you choose. And that's what a fixed value means. So these are fixed. Dr. Shafkan's also talked of stochastic regressors, but we're not considering them here in this subject, omission of relevant variables. I mean, you can think about them as well, but it's just not necessary to understand the subject of omission of relevant variables, and it just adds extra complications to it. So we're just thinking in the framework of fixed, something you choose. What is beta and delta? I keep calling it delta, but it's gamma. So what's beta and gamma? They are they're also vectors, and they are vectors of constants. So beta will be A, B, C, D, and these are constants, or if you want to call them beta 1, beta 2, beta 3, and so on. These are constants. So these two are constants. Epsilon, on the other hand, is a random variable, which we will assume it's normally distributed with some mean and variance. I mean, we know what they are, so the mean is going to be 0, and according to our assumptions, so this is assumption 3 of Gauss-Markov assumptions, and which is the expectation of epsilon is 0, and this is assumption 4, which says it is going to be a sigma squared I. So the I, well, okay, this just means a matrix with zeros here, and just a diagonal of sigma squared. So they all have the same variance. Well, first of all, why is it a matrix? Well, because sigma is a vector, and it has sigma 1, sigma 2, sigma 3, and this diagonal represents the variance for each of these. So sigma, well, the element at 1, 1 is for the variance of epsilon 1, and this one here at the end is the variance of this last epsilon here. Okay, that aside, let's just erase all of that. So it's normally distributed with a mean of 0 and a variance of sigma squared I. So this is the true model. Well, let's talk about y as well. It's also a vector, and because it is a linear combination of a random variable, which is epsilon, it is also a random variable. Okay. Now let us drop the z, which is the relevant variable, well, a relevant regressor, let's say, and see the consequences. So let me use a bolder pen. Let's use this regression. Y equals x beta plus, well, here the error term is going to take other values, and we're just going to call it v because we've dropped z. So what does this mean? What does dropping a regressor means? So in the first model, in the true model, we're collecting data that include x, z, and y, and that is a collection. So for each x and z there is a y, and you get data filling these up. In here you drop the z, so you're just collecting x and y, pairs of data. So you're not distinguishing any z variable here. And that's what it basically means. So now let's try to see what the estimator of beta will be, using only these pairs of data instead of the triples of data in the x, z, y case. So if we try, based on the if we try to calculate the OLS estimator based on the pairs of data here, we will get so this is the estimator for beta. Remember, beta is a constant, it's a parameter of the model. So if we want to get its value, we have to estimate it using a random variable, and beta hat is a random variable. So beta hat is equal, we know that it's going to be equal to x prime x inverse x prime y. Now we know y is actually equal to that at the top in the true model. So let's substitute that then. See what we will get. So it's x beta plus z gamma plus epsilon. Now we can see that, okay, let me expand it actually. So x prime x inverse x, so there should be a prime here, prime x beta plus this again z gamma plus again x prime x inverse x prime epsilon. Great. Now let's try to simplify that. So we can, if we group these together and multiply them together, we get some matrix, and if we then we can see it's the inverse of this matrix, so the result of this multiplication is I, and that's the best we can do to simplify that. Now, to see where beta hat, which is the estimator of beta, is centered, or let's say what value does beta hat is trying to, what value is beta hat trying to approach? That's the other way of saying what's the expectation of beta hat. Okay, so let's take the expectation of beta hat. Well, an expectation, so basically we're getting the expectation of this expression. We only have beta I here, and that's just a constant matrix, so we get beta only because that's just constant, plus, okay. Now, as we said, the x's are fixed by us. We're choosing them to be one value, not random. Z is the same. Gamma is just a vector of constants. So this is just the expectation of something constant is a constant, is the constant itself. Gamma. Plus, well, again, the same case here, x prime, x, well, all the x's are fixed, so take them out of the expectation. And we are left with the expectation of epsilon. Now, remember what we said here. Epsilon is a random variable, and it is randomly distributed. It's normally distributed this way with an expectation of 0. So, expectation is 0. So this whole term drops out. So we're left with the expectation of beta is actually, the expectation of beta hat is actually beta, which is what we hope it would be, but there is a bias of x prime x inverse x prime z gamma. Now let's think what this bias means. What is it trying to tell us? Let's take the first part. This looks familiar. This looks like this, except y is substituted by z. So it's like we're saying that this term is the estimator for OLS, well, it's the OLS estimator for a parameter in here. So if we regress z, I'm just trying, so if this is, I don't know if my pointer is clear, but let me use the mouse. If this is an estimation for the parameter beta in here, so this is an estimation for the parameter in here. Let's call it phi plus some error. Okay, so it's an estimator for phi. We can call it phi hat, but it's an estimator for phi. And what's the other one? Well, we know from the true model that gamma is the parameter for z, which means it's the marginal effect of z on y. So for example, if z increases, y increases by that much. That's what gamma is. So it's a multiplication of phi hat by gamma. Well, what does that mean? What it is saying is that the value that beta hat is trying to approach in its estimation of beta is going to be equal to beta itself, but with an additional bias, the bias being the indirect effect of x on y through the path of z. That is, if x increased z by phi hat, by phi hat, and then z increased y by gamma, then you get this effect, the indirect effect of x, because x is increasing z by that much, by phi, and then z is increasing y by that much, gamma. Okay. Then, as a result, in order to get this, so in order for this bias to exist, first of all, gamma has to be not equal to 0, which is saying that z actually affects y, i.e. z is relevant to y. And the other condition is that phi hat, phi hat is trying to estimate phi, so let's say phi is not equal to 0, which means x affects z. Okay. So we've discussed the value of beta here. It's going to be biased by an additional effect, which is the indirect effect of x on y through z. But okay, we are estimating beta by beta hat. But how precise is beta hat? How precise is it to give us this value of beta plus the indirect effect? Okay, so in order to do that, we're going to get the variance, of course, because precision is related to variance. So let me mark that. I'll call it precision of beta hat to get beta plus phi hat. So this is a value, and this is what beta hat is trying to approach, but by how precisely is it trying to approach it? So variance of beta hat. So instead of doing that all over again, I'm just going to start from this here, because that's what beta hat is, what we worked it out to be. So I'm just going to copy it actually. Okay, copy, paste. Okay. So it is the variance of that. Equals the variance of that. Well, we know that this is, the first term is just beta, which is a constant, so it just drops out, because the variance of a constant is a constant, obviously. This is fixed, so it drops out, same reasons. But we have a random variable here, epsilon, multiplied by a constant. So they both go to the next step, variance of x prime x inverse x prime epsilon. Well, what's the variance of a constant multiplied by a random variable? In the non-matrix world, so to take the constant out of the operator, it's the constant squared. But with matrices, we have an equivalent to squaring something, which is to multiply it by its transpose. So we get x prime x inverse x prime, the variance, we're left with the variance of epsilon, and then the transpose x. Okay, so we start from here, because in transposing we start from the end. So x transpose of x. So the transpose of a transposed x is x, and then the transpose and the inverse operators are exchangeable, like swappable, because the inverse of a transpose equals the transpose of the inverse, and we proved that in MA100 last year. So we get, so what's the inverse of x prime x? It's the same, x prime x, and the inverse of that. Now if we go back, what's the variance of epsilon? We said it's normally distributed with an expectation of 0 and a variance of sigma squared I. Alright, so that's an easy result. So this is sigma squared I. If we multiply I by x, we get x, so I goes away, and sigma squared is a constant, so just bring it wherever. Sigma squared x prime x inverse x prime x prime x inverse. Now if we group that together, and we can see it's the inverse of the first term or second term. So if you multiply these together, you get I, and I drops out because I times this is itself. So sigma squared x prime x inverse. Now what does that mean? Is that good? Is it less precise than estimating beta in the full model, in the true model? Well, no, because we know from previous lectures that the variance of beta hat in this true model is sigma squared x prime x inverse. So the precision is the same of beta hat if we know sigma squared. But do we? In most cases, we don't know what sigma squared is, and we just rely on the data to estimate sigma squared. So our estimation of sigma squared actually depends on the data. And to estimate sigma squared, we use, so estimate of sigma squared equals S. We call it S squared. I mean, it can be called sigma squared hat, but we call it S squared. And so this is a random variable for a parameter. This is constant. Sigma squared is constant. S squared is a random variable because it's random. It relies on the data to it basically relies on another random. So we said that y is a random variable, but x is constant. But because y is a random variable, then s squared is a random variable. Now, we said we're going to use the short model, and that means we're going to collect x and y only, pairs of x and y's, not triples of x, z, y's. So we have less information. So we know, we've proved before that s squared equals to, well, it's the realized values of the error term. So, you know, in the short model, we called the error term as v. So it's the realized value. Remember, v is a random variable as well. But v hat is the realized value of this random variable. It's like when we used to write small x for large X in ST102, being that x, small x, is the realized value of x, big X. Okay, so this is equal to v prime v hat, over n minus k, n being the number of observations, and k is how many parameters, how many regressors we have. And this is not going to be, this is going to be a biased estimator of sigma squared, and therefore, I mean, we're not, as Dr. Shavgans has mentioned, we're not required to prove that, so I'm just going to leave it at that. We have less information. These are not going to be are not going to meet our assumptions, being that they don't have an expectation of 0, and that's going to mess up with our estimation of sigma squared. There will be bias. Therefore, if we use s squared instead of sigma squared, the variance of beta hat, so the precision of beta hat, is going to be less, because our estimation of sigma squared was wrong, was biased. Okay, so this finishes our talk about the emission of relevant variables. I hope that was helpful and clear, and hopefully it added some new things to your understanding. And thank you for watching. I will be carrying on with the next subject, which is the inclusion of irrelevant variables.